As we got familiar with power functions, now we can move to another section, which is polynomials. So monomials, when we just had x to the power of m, and when we have several of them together, then it's called polynomials. So main form of polynomials is sum of several monomials. We call them polynomials to degree n. So depending on what is n here, for example, is equal to 2, then degree will equal to 2. We will say polynomial of degree 2, degree 3, degree 4, all depending on what kind of n we have here. And of course, our coefficient an should not be equal to 0, and our domain will be all real numbers. Polynomial can be also, for example, if we have p0 of x equal to 2, if you can see here we have no xn in this function, then this will be just constant, and we call it polynomial with degree 0. So it looks like this on the graph. So it's a constant which is equal to 2, and it will look like this. Also, for example, polynomial of degree 1 will look like this. P degree of 1 will look like 2x plus 2. You see here degree is 1, and polynomial with degree of 2 will be something like 3x squared plus 2x plus 3. This will be the polynomial of degree 2. The graph of polynomials will depend on the highest degree and the lowest degree that we have. As x approaches plus or minus infinity, then the polynomial will behave more like a larger power. And as x is closer to 0, then behavior of polynomial will look like a smaller power. I think it's a little bit not clear, but trust me, we will look at the picture now and it will get better. So, for example, we have here polynomial of degree 5, 3x to the power of 5 plus x squared minus 6x plus 2. So let's say we have this polynomial. So to imagine its graph, we will have to first look at the largest and to the smallest summand. The smallest graph will look like this as a line, and the largest one will look like this. And our polynomial is somehow the sum of both. Roughly, if we want to make a picture of how it looks, if x tends to 0, it will tend to look like a smallest power. Smallest power here is just a line, straight line. So it means somewhere here it will behave like this, around 0. But then the more x approaches minus and plus infinity, it will behave like larger power. So then it will kind of curve towards here and go towards here. So our polynomial in the end will look something like this, as a sum of both. And if we look at the nicer example here, so this is again our line minus 6x plus 2, and here we have 3x to the power of 5, and our polynomial is exactly kind of sum of both here in the red line. So next, what I wanted to talk about roots of polynomial. The polynomial of degree n have as most n roots. So polynomial with degree 2 will have at most 2 roots, at 5 will have at most 5 roots. Odd polynomials have at least 1 root, and polynomials that consist only of summands with even powers with coefficients larger than 0 will not have any roots. Now let's have a look at examples. 5 is the largest power here, and our polynomial is of degree 5. So we have 1, 2, 3, 4, 5 roots here. Roots is where our function is crossing x-axis. So these are the roots of polynomial. Odd polynomials have at least one root. For example, here we call it odd polynomial because the degree of odd polynomial is 5. And 5 is an odd number. And as shown in this example, it crosses the x-axis in one place. It means that we have only one root. But generally, polynomial with a degree 5 can have up to 5 roots. And in this current example, we have only one root. And sometimes polynomials consist only of summands, for example, 2x to the power of 4 plus 2x squared and blah 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 with even powers, plus the coefficients a0, a1, a2, etc. larger than 0 will have no roots. It will just mean that they will never touch the x-axis. For example, here we have polynomial with only even powers. And a0 is equal to 4. So here you see they just don't touch x-axis. That's why they don't have any roots. In previous chapter, we saw how to solve the roots of quadratic equations with the help of PQ formula or completing the square or Vieta formula or whatever ABC formula. We had like a lot of different methods how to find the roots of quadratic equation. For general polynomials of higher degrees, starting from 3 and higher, there aren't any useful formulas for calculating the roots, unfortunately. In certain special cases, the root can be still calculated, and I will explain a few typical examples. So, for example, substitution. We did it already in the previous chapters. For example, here we could replace x squared with another letter u, and then we write as u squared minus 13u plus 36. And then solve it with using PQ formula. You can pause the video and try to find it with the PQ formula as we did a lot of time before, and then come back to me and check the answers. All right, welcome back. And we'll quickly calculate it. U1 and U2 as 13 divided by 2 plus minus square root of, again, 13 divided by 2 squared minus 36. So discriminant in this case will be positive, and then we will have U1 equal to 9 and U2 equal to 4. X squared is equal to U1, and x squared will be equal to 9, and x1 and x2 will be equal to plus minus 3. And x squared will be equal to U2, and x squared is equal to 4, x3 and x4 will be equal to plus minus 2. And set of roots for this polynomial will be minus 2, minus 3, 2, and 3. So at this point, our function will be crossing the x-axis. The next example here, we can rewrite it as x to the power of 5 minus 4x to the power of 3 equal to 0. We can, for example, bring x3 out of brackets, minus 4, and this, if you remember binomial formula, according to binomial formula, we can rewrite it as x minus 2 and x plus 2. And here, if it's 0, then one of them should be 0. And for this example, we will have set of roots equal to 0, 2, and minus 2.